In this video, I'll explain how to perform early power estimation for PolarFire FPGAs using the Microchip Power Estimator. Modern FPGAs have much higher performance than previous generations. This higher performance leads to higher power consumption with more stringent thermal constraints to ensure that the design remains within the thermal limits of the system. Power consumption is an important part of the equation determining the end product's size, weight, and power, or SWAP. Low power consumption provides several benefits, such as elimination of heat sinks and fans, which can reduce the total bill of materials and improve overall reliability. Fans are noisy and can fail, leading to a failure on the board, which negatively impacts the product's reliability. Lower power consumption supports applications in small or sealed enclosures and provides thermal headroom for more compute capability for network edge computing applications. Low power consumption leads to longer battery life for handheld or portable equipment, which can be a competitive advantage. Low power devices can be produced in smaller packaging, allowing them to be used in applications with small form factors where fans and heat sinks won't fit. Lower power consumption has positive system implications that go beyond battery life. Lower power consumption results in lower self-heating, so the device will remain cooler. This is important because semiconductor devices are specified for a specific operating range with a maximum junction temperature of typically 85 degrees C, 100 degrees C, or 125 degrees C. At this temperature, all timings inside the device are still guaranteed. If the temperature is exceeded, functional failures in the design might occur. Additionally, one of the important aging factors in semiconductors is high temperature. Devices running at higher temperatures will age quicker and reliability of the whole system is reduced. This decreased reliability directly impacts the mean time to failure, or MTTF numbers. MTTF is an important aspect in functional safety. Devices that have strong self-heating also stress the board material and affect neighboring devices. Neighboring devices are heated up and will consume more power if they are semiconductors, potentially suffer some secondary aging effects, and may be affected in their accuracy. For example, image sensors with more noise at higher temperatures. The system thermal budget, or system cooling, may be limited. If a device with low power consumption and lower self-heating is used, more features can be implemented. These additional features require logic inside the device and consume power. With lower power devices, more work can be done and more features can be added, allowing the client to reduce risk, save money, and make money. Power consumption is important for functional safety. Functional safety is concerned with failure rates. A design that involves functional safety is not built to not fail. Sooner or later, and later can be a very long time, it will fail. The important thing is that the device has to fail safely, and there must be an estimation on the likelihood of a system failure. The likelihood of a system failure is measured in fit rate, or failure in time. One fit equals one failure every 1 billion hours of operation. The lower the fit rate, the lower the probability of a device failure. The hardware fit rate depends on temperature. The lower the temperature, the lower the fit rate. A general rule of thumb is 10 degrees C temperature reduction approximately halves the fit rate of a design. A higher fit rate in hardware makes it harder to achieve safety certification. This slide shows a comparison between a PolarFire FPGA, a Kintex 7 FPGA, and an Area 5 FPGA implementing two different designs. These comparisons show that the PolarFire FPGAs consume up to 50% lower power than the best-case competitor. A client said they were able to reduce their BOM costs by $1.50 per watt using PolarFire FPGAs. Lowering the power consumption can result in considerable savings for a client. The power message is also emphasized by looking at vendors' FPGA development boards. Microchip's FPGA and SoC FPGA boards don't require fans or heat sinks. Nearly every competitor's demo board has a fan or a heat sink, which is not required on Microchip's boards. Next, I'll describe the steps to properly estimate the power consumption. The Microchip Power Estimator can be downloaded from the Microchip website. The power estimator can be manually filled with an estimate of the resources used in the design, such as flip-flops, LUTs, RAM blocks, transceivers, and IOs, or with data exported from Smart Power for implemented designs. Power analysis should always be done with worst-case conditions. There is no guarantee that a customer will receive only typical process parts, and as such, a customer doing power or thermal analysis should always design their system with the assumption that some percentage of their received parts will be worst-case process. If they design a system for only typical process, they're in danger of failures. It's also important to do ambient temperature sweeps to see how much the power and the junction temperature increases as the ambient temperature increases. Device self-heating is important and needs to be considered. In the Microchip Power Estimator thermal input section, the default calculation mode is user-entered junction temperature, or TJ. To observe the device self-heating, change the calculation mode to estimated junction temperature. You will also need to enter the thermal conductivity for the board. After entering the design data, do the ambient temperature sweep by entering different values for the ambient temperature. This will allow you to graph the junction temperature versus ambient temperature and observe the self-heating. So how do you do thermal sweeps? You can do them manually and record the data, or you can use a macro that's available from the Microchip FPGA BU business development team. The macro takes the data from the Microchip Power Estimator and the Xilinx Power Estimator and runs a thermal sweep on the devices to provide direct comparison of power consumption and device self-heating. Let's look at the design I'll be using with the Microchip Power Estimator. The demo design consists of an FPGA fabric logic block and a transceiver block. The FPGA fabric block contains an array of 18 by 18 multipliers, logic that writes and reads RAM blocks, and logic that drives LEDs on the board. The PF init monitor block monitors the device initialization sequence and asserts signals indicating that blocks have been initialized. The core reset PF block combines the resets from multiple sources, such as external general purpose IOs, PLL lock signals, and the PF init monitor block, and synchronously deasserts the reset to the downstream logic. The transceiver block has two lanes running the 10G base R protocol at 5 gigabits per second. The lanes are looped back on the PolarFire kit. A pattern generator implemented in the FPGA fabric provides the transmit data, and a pattern checker implemented in the FPGA fabric checks the receive data and generates an error if the received data doesn't match the transmit data. One of the PolarFire PLLs is used to generate a 200 MHz clock for the FPGA fabric and a 40 MHz clock that drives the transceiver enhanced receiver management logic, or ERM. The ERM manages the receiver calibration. The PLL reference clock is the PolarFire 160 MHz RC oscillator. An external 125 MHz oscillator provides the transceiver reference clock. The demo design is implemented in a PolarFire MPF300T 300,000 LUT FPGA in the FCG 1152 package in the industrial temperature grade. The fabric logic consists of 198,000 LUTs and 217,000 D flip-flops. There are 200 LSRAM blocks, 200 micro SRAM blocks, and 200 math blocks. There is one LVCMOS 18 input and 5 LVCMOS 18 outputs. The transceiver block has two lanes running 10G base R at 5 gigabits per second. The D flip-flops, math blocks, and RAM blocks in the FPGA logic block are clocked at 200 MHz. There is also a 40 MHz clock for the transceiver control logic. An external 125 MHz oscillator provides the transceiver reference clock. The objective of this demo is to calculate the power consumption for the design using the Microchip Power Estimator for PolarFire. This is the Microchip Power Estimator for PolarFire. The Power Estimator workbook has multiple worksheets. The summary worksheet is where you input device settings and power rail details. The summary provides an overall view of the power estimation and displays any errors that exist in the data entered. The analysis worksheet provides the power breakdown, static power, dynamic power, and total power, and the power breakdown by resources: clocks, logic, math blocks, RAMs, IOs, PLLs, and transceivers. The worksheet provides a comparison of data entered in the Power Estimator and a worksheet exported from the LibreSoC Smart Power tool. You can also import an XPE file for Xilinx FPGA designs to compare the power consumption with PolarFire. The Graphs worksheet displays a graphical representation of the static current and on-chip power. The Snapshot worksheet displays power consumption data captured at various points in time for future reference. The Current Breakdown worksheet displays functional static current, inrush current, programming current, and zeroization current. The feature-specific worksheets contain power and utilization data for specific device features such as clocks, logic, LSRAM, microSRAM, math blocks, IOs, transceivers, PLLs and DLLs, and security blocks. The user worksheet is a blank worksheet where calculations can be performed and notes can be entered. Here I am back at the summary worksheet. There's a toolbar at the top of the worksheet that has several buttons. The Import button opens the Import Data into MPE wizard, which allows you to select an existing Power Estimator worksheet or a worksheet exported from the LibreSoC Smart Power tool. The Initialize Power Estimator button opens the Initialize Power Estimator wizard, where basic design data such as system clock frequency, number of designed resources, I/O technology, and toggle rates can be entered for quick and easy power estimation. The Manage IP button opens the MPE IP Manager wizard, which allows you to add or delete any IP used in the design. Values entered are automatically populated in the various feature-specific worksheets, and the Power Estimator results are updated to include the IP resources. The MPE IP Manager has two tabs. The Create IP tab allows you to create block memory, memory interfaces, and transceiver interfaces. The Manage IP tab allows you to delete any previously created IP blocks. The Create Snapshot button captures a snapshot of the current power estimation data and saves it for future reference. A maximum of 10 snapshots can be saved. The Reset to Defaults button opens a window with options to reset the data in the Power Estimator workbook to default values. There are several reset options available. The Export Report button opens a window with options to export the Power Estimator data in a text file. Users can specify the data to be included in the report. The Import XPE File button allows you to import an XPE file for Xilinx FPGA designs to compare the power consumption with PolarFire. All the cells in each worksheet of the Power Estimator are color-coded to simplify data entry and review. White cells are editable fields where data can be entered. Gray cells are non-editable description fields. Light gray cells are fields that are not applicable because of previous selections. Green cells are read-only computed summary or total values. Light green cells are read-only calculated values. Red cells indicate input errors. Orange cells indicate there is a warning for the data entered. Now that I've described the Microchip Power Estimator, let's enter the numbers for the demo design. First, I'm going to reset the Power Estimator to the default settings by clicking Reset to Defaults, then selecting Reset All Settings and Snapshots. Next, I'm going to choose the die and package. I'll use the pull-down menu to choose the MPF300T, choose the FCG1152 package, and the industrial temperature range to match the silicon on the PolarFire splash kit. For core voltage, I have a choice of 1 volt or 1.05 volts. I'm going to use 1 volt. For process, I'll choose maximum. As described earlier, power analysis should always be done with worst-case process. There's no guarantee that a client will receive only typical process parts, so when doing power or thermal analysis, they should always assume that some percentage of their received parts will be worst-case process. If they design their system for only typical process, they're in danger of failures. For speed grade, I'll choose the -1 speed grade, which matches the silicon on the PolarFire splash kit. The thermal input section shows the method used to calculate the junction temperature. The default setting is user-entered TJ, which allows you to specify the junction temperature. The estimated TJ setting calculates the junction temperature based on user-specified thermal inputs. When the estimated TJ option is selected, the user enters the ambient temperature and the estimated junction temperature is calculated. A heat sink can be selected and the ambient airflow can be specified if the junction temperature exceeds the maximum. Selecting estimated TJ allows running temperature sweeps by increasing the ambient temperature and observing the increase in power consumption and the junction temperature. Running temperature sweeps can identify limits to the device power models and provide information about the device self-heating. After selecting estimated TJ, I'll enter 25 degrees C for the ambient temperature with no heat sink and still air. Next, I'll click Initialize Power Estimator to initialize the power estimator with the data from the design. For the system clock, I'll enter 200 MHz. For flip-flops, I'll enter 217,000. And for LUTs, I'll enter 198,000. The demo design has 200 micro SRAM blocks, 200 LSRAM blocks, and 200 math blocks. The design has 1 LVCMOS 18 input and 5 LVCMOS 18 outputs. The toggle rate specifies the switching activity for the design. Competitors' power estimators default to 12.5% toggle rate, so when doing a direct comparison against a competitor's power estimator, the default rate can be used. However, it's important to use a realistic toggle rate and RAM enable rate for an accurate power estimate. I'm going to use the default toggle rate of 12.5% and the default RAM enable rate of 12.5% for this demo. I'll click Reset and Initialize to reset the power estimator with the data I entered. So now most of the values for the demo design have been entered into the power estimator, and I can confirm the entries on the feature-specific worksheets. The clocks worksheet shows the 200 MHz system clock. The logic worksheet shows the clock frequency is 200 MHz, 217,000 D flip-flops, and 198,000 4-input LUTs. The LSRAM worksheet shows 200 LSRAM blocks with a clock frequency of 200 MHz. The memory width in the demo design is 18, but the pull-down menu doesn't have 18, so I'll use 20. I'm going to leave the other settings, the write mode, write rate, read rate, and enable rate, at the default settings. For early power estimation before implementing the design, it's okay to use the default RAM settings like pipeline registers. After implementing the design, ensure the settings match the design by exporting a report from LibreSoC and importing it into the power estimator, or by reviewing the configurator settings and design reports, such as the Simplify RAM block usage report. Looking at the micro SRAM worksheet, there are 200 micro SRAM blocks and the frequency is 200 MHz. I'm going to accept the default width of 12 and the default settings for the write port and the read port enable rates. Remember to change these settings if needed to match the implemented design. The math block worksheet shows the frequency is 200 MHz and 200 math blocks are in the design. In the demo design, the math blocks are used as a normal multiplier, so I'm going to accept the default settings. For accurate power analysis, confirm the math block settings match the design. The I/O worksheet shows one LV-CMOS18 input and 5 LV-CMOS18 outputs. I'm going to change the default output drive to 8 mA to match the default settings in the Libro SoC I/O editor. I'm not using any of the digital features in the I/O block, so I'll accept the IOD mode unused. I don't have any settings for the transceiver, so I'm going to enter them on the transceiver worksheet. I'll enter a name for the transceiver block. There's some transceiver protocol presets, but I'm using 10G base R, which is not in the list, so I'll just leave the protocol blank. The demo design uses 2 lanes in full duplex mode at 5 gigabits per second. I'll accept the default signal integrity settings. Finally, on the PLL and DLL worksheet, I'll enter a name for the PLL, then enter the PLL reference clock frequency, which is 160 MHz. The PLL output frequencies are 200 MHz and 40 MHz. The summary worksheet displays the power consumption. The total power is 2.838 watts with 263 milliwatts of static power and 2.494 watts of dynamic power. The junction temperature, or TJ, is 47.71 degrees C. The summary also displays the thermal margin for the design. For the cooling scenario I selected, the maximum ambient temperature, or TA, is 72.38 degrees. The power breakdown shows the individual contributors to the power consumption. This information can be helpful in determining the source of power consumption if the power budget is exceeded. Now that I have the power estimate, I can create a snapshot. We can refer to these numbers later, particularly if I want to make any changes to the die, package, or cooling scenarios. The graphs worksheet displays a graphical representation of static current by power supply, typical versus maximum power versus junction temperature, and total power versus the supply voltage. There is also a pie chart showing the power breakdown. Here is the snapshot that I saved. The snapshot shows the power data and other information that was entered, such as die, package, and environmental conditions. I can give the snapshot a name. I'll call this Estimate 1. You can delete snapshots and you can restore the snapshot. Temperature sweeps are an important part of power analysis. They can provide information about device self-heating and identify limits to the device power models. I'll increase the ambient temperature and observe the change in the power consumption and the junction temperature. If I enter 30 degrees C without any other changes, I see the total power is 2.871 watts and the junction temperature is 52.97 degrees C. I can save a snapshot of the results. I'll continue changing the ambient temperature and create a snapshot for each result. For this design, if the ambient temperature exceeds 72.38 degrees C, the junction temperature will exceed 100 degrees C. If I enter 75 degrees C for the ambient temperature, the junction temperature is 104.52 degrees C. The cell in the power summary is highlighted in red, indicating the junction temperature exceeds 100 degrees C. If the junction temperature exceeds 100 degrees C, a heat sink and airflow can be selected, and the power estimation can be repeated. To demonstrate, I'll select a 15 mm medium profile heat sink with still air. With the heat sink selected and the ambient temperature of 75 degrees C, the estimated junction temperature is 91.87 degrees C. Note that the maximum ambient temperature, TA, increased to 82.37 degrees C. I can perform a temperature sweep with the heat sink selected like I did without the heat sink. I plotted the power consumption and junction temperature versus ambient temperature on the user worksheet. The graphs show the junction temperature Tj versus ambient temperature Ta and the delta temperature versus ambient temperature, which shows the device self-heating. Microchip has developed an Excel-based power comparison tool that can be used to compare the power consumption between PolarFire FPGAs and Xilinx FPGAs. All that's required to compare power consumption is an XPE file, which can be exported from the Xilinx Vivado tools. The power comparison tool automatically runs thermal sweeps and generates diagrams, which allows direct comparison on power and self-heating. The tool can also be used without an XPE file to run temperature sweeps for the PolarFire device using the data entered in the Microchip Power Estimator. I'll demonstrate running the automatic temperature sweeps for the demo design. This is the power comparison tool. The Transfer tab is where you enter information regarding the PolarFire design and the Xilinx design. The User Guide tab has links to the Microchip and Xilinx power estimators and the steps required to run the power comparison. To perform temperature sweeps, the power estimators must be open. For the demo design, I'll enter the name of the Microchip Power Estimator containing the design information, then click Create Power Sweep. The power comparator will sweep the ambient temperature from 20 degrees C to 95 degrees C and record the total power and junction temperature of the device. It will take about a minute to complete the temperature sweep. When the temperature sweep is complete, I'll select the MPF300T Only tab, which shows the results for the demo design. The tab contains tables and graphs showing the power consumption versus ambient temperature. The first graph shows the power consumption versus ambient temperature for typical and maximum operating conditions. Scrolling down, there's a graph showing the delta temperature, which shows the self-heating of the device. The third graph shows the absolute junction temperature versus ambient temperature. The graphs allow designers to see the power consumption versus ambient temperature and to observe the self-heating and thermal margin for the design to help determine if a heatsink or other cooling method is required. In this video, I explained how to use the Microchip Power Estimator to get an early power estimate for a design and how to directly compare power consumption between PolarFire FPGAs and Xilinx FPGAs. The key steps to performing power estimation are to select maximum process settings in the power estimator and select estimated junction temperature in the MPE thermal input section to allow the junction temperature to be calculated based on the ambient temperature and to perform ambient temperature sweeps as part of the analysis. The MPE uses default toggle and RAM enable rates of 12.5% to match the competitor's tools. The toggle rate might need to be changed to more realistic values based on the type of data expected to flow through various parts of the design data path and control path logic to get a more accurate power estimate. I also introduced the Microchip Power Comparison tool that can be used to compare the power consumption between PolarFire FPGAs and Xilinx FPGAs. The tool automatically performs temperature sweeps and provides graphs showing power versus ambient temperature, junction temperature versus ambient temperature, and the device self-heating effects. Now that you've viewed this video, download the Microchip Power Estimator and try it for yourself.